Okay, hello, DC Theory class for fall term 2020. We're going to do these continuing. This is my week that I am not going to be able to be present for the Zoom class, so this is the video that I'm going to ask you to watch in lieu of our normal lecture. And this week I want to go over series circuits. Now, the circuit that we did in class last week was technically a series circuit. It was a funny series circuit in though it was the simplest, in that it was the simplest circuit. It had only one resistor. And the way we tell a series circuit from a parallel circuit is the way that the resistors are oriented to each other and in fact to the power source. So let's just go ahead and take a look at that simplest circuit one more time. Again, when I draw a circuit, I'm going to draw a power source. I'm probably going to label that power source with some sort of voltage. In this case, I'm going to say it's 100 volts DC. Because that's what we're working with right now is DC theory. And I'm going to draw the circuit out. So these are the conductors. And I'm going to draw it out. And I'm going to have a resistor, in this case, only one resistor in the circuit. And we're going to see how all of the relationships work within this circuit with only one resistor. Now, I've given it a voltage. I can give this resistor some value. Last week I did really easy numbers. Let's do a little bit more difficult numbers. Let's go and say this is like 3 ohms. So I'm probably going to have to use my calculator on this one. Because to determine the current on this, if I know my resistance and I know my voltage, I can find the current out by using the Ohm's law wheel. We went over this last week, and I know that my current, I, is going to equal my voltage, E, divided by my resistance, R, which is going to be, in this case, 100 volts DC divided by 3 ohms. So if I punch those numbers into my calculator, which I probably could do in my head here, but I'm going to go 100 divided by 3, and that equals 33.33 continuing. So my current is 33.33 continuing is how I write that. Your calculator just shows you 3's forever. Also, if you know it, this is actually 33 1/3. 33 1/3 amps, but we're going to stick in decimal, call it 33.33 continuing. You could also just round it down to 33.33 amps. That would be fine too. And we've solved that circuit. That's easy enough. The thing to notice about this circuit and any series circuit, and why I'm going to call this the simplest series circuit, even though really that resistor isn't in series with anything other than the power source, is there's only one load. Every series circuit will have one current path. In fact, that's the rule to determine that it is in fact a series circuit. If there were 2 different ways for current to flow, this would not be a series circuit. Say, if I had another wire that connected that to that, well, it's no longer a series circuit. In fact, it's a short circuit. I've just created a short circuit on that. If instead I had another resistor here, so I had 2 resistors, which we'll learn later is parallel. Now I've got 2 paths for current to flow. Current can go that way and current can go that way. It's no longer a series circuit. Let's go ahead and look at a little bit more complicated series circuit just so we can get our heads around this. And we'll talk about the rules for a series circuit. So I'm going to go ahead and draw a very similar circuit to that. I'm going to say it's 100 volts still, just because that's a nice easy number. And I'm going to put 2 resistors in this circuit. And those 2 resistors, you'll notice before I even give any value, those 2 resistors are in series with each other because if I'm an electron, I have no choice, and if I'm running around this circuit, I have no choice but flowing through this resistor and this resistor. Every bit of electricity that flows in this circuit will flow through both of those resistors. There is only one path for electricity to take. Now remember, the reason electricity is flowing is because I have this voltage source. And if I'm an electrician, I'm going to ground this side so I can call this voltage 0. By grounding this, I've said, okay, I'm deciding this is my reference voltage at 0. Remember last week we talked about a voltage is the difference between 2 points. So the difference between this point and ground, there is no difference, so it's 0 volts. The difference between this point and ground is the 100 volt source. That 100 volt source makes this up here 100 volts. So now if I take my voltmeter, let's get a different color here. If I take my voltmeter and place one probe of my voltmeter anywhere on that point, and I put the other probe of my voltmeter anywhere on this point, I'm going to have the difference between 100 volts and 0 volts, which is 100 volts. 100 minus 0 is 100 volts. Any place on this and any place on this this is all the same point, is 0. This is all the same point, was 100. Now this point here between the two resistors, I'm not sure what that is yet, and that's part of what we're going to be deciding on this. But that's an interesting and important thing to remember about voltage. Now some of you may say, yeah, but doesn't the wire itself have some resistance? And the truth is, yes, the wire has some resistance. And so in reality, I would actually have to model this as the whole thing being a resistor. But for the purposes of us discussing this and doing analysis on this circuit, we're going to call this wire a perfect conductor. For the sake of our model and for understanding the circuit, we're going to say that when I draw a line, when I draw a conductor with this magic marker, that's the perfect conductor. Better even than silver, which is the best conductor. And it has 0 resistance. Now in reality, is there a conductor with 0 resistance? No. Every conductor has some resistance. But for the sake of these models, that's what we're going to think of them in. So back to this circuit. I know that there's only one current path, and that's the way I know that this is a series circuit. So much so that I'm going to make that the first rule. So over here I'm going to put some rules for series circuits. Now this is really, really important. If you're going to take notes on any of this or record any of this somehow, record this part. Record the rules and know the rules and learn the rules, because if you get the rules, you'll be able to do all this stuff. For a series circuit, let's even put that up here. Series CKT. CKT is my shorthand for circuit, electrician shorthand for circuit. Rule number 1, series circuit is identified by one current path. One and only one current path. If I'm an electron traveling this circuit, there's only one place I can go. I don't get any T's or any place that I can choose to go one way or the other. I have one current path. Because I have one current path, and because of the way electrons work that we learned last week, I'm going to have the same current everywhere in this circuit. If I can determine what the current is here, or here, or here, I know that's the same current everywhere. Because think about it, if amps are just counting electrons, I'm counting 6.25 times 10 to the 18th electrons that pass a point per second, right? Remember that was what we decided the definition of an amp was. So an amp is just a quantity of electricians passing something at a point. And in order for those electricians to pass the point, they need to push other electricians down the road. Remember the bump theory? Bumping one electrician to bumping one electron to the next atom or molecule and so on. So I know that when current is flowing here, it's also flowing here, it's also flowing here. In fact, we can say to ourselves in our model, all the electrons that pass through this resistor are also going to pass through this resistor. They're the same current. So if I find out what the current is here, it's the same current as here, it's the same current as here. So that is a rule of a series circuit. And that's a really important rule because that rule allows us to solve a lot of things. We know that current is the same at all points in circuit. That's going to help us a lot. Current is the same at all points in the circuit. Well, now I've got to actually start doing some analysis here, don't I? So I better give myself some values to these resistors because I don't know the currents and I know the voltage, so I'm going to have to take the resistors as a given. So I'm going to say that this resistor is 20 ohms, and I'm going to say this resistor is 5 ohms. I'm going to call this R1 and I'm going to call this R2. So I've got two resistors that I've decided are in series. They're in a series circuit. I know that because they're in part of the same current path. And I've called them R1 and R2. This resistor is a 20 ohm resistor, and that's an inherent characteristic of that resistor. If I were to pull that resistor out of the circuit, set it on the desk, put an ohm meter on it, it would still have 20 ohms. It doesn't have to do with the way I've put it in the circuit. That's an inherent trait to that resistor. up until the point that I let the smoke out of the resistor. That is, I burn up the resistor because I push too much power through it or something, which you can do. You can destroy a resistor that way. You probably have all seen electronic gear that's smoked. If I smoke this resistor, it's no longer going to have 20 ohms. But up until that point, pretty much we can say it's a 20 ohm resistor. Now, that fluctuates a little bit with heat, and that resistor gets hot right when I pass current through it. So again, for our model's purposes, 20 ohm resistor is a 20 ohm resistor, a 5 ohm resistor is a 5 ohm resistor. Now, when I am an electron traveling in this circuit, I'm being pushed through these resistors by this voltage source which supplies the pressure. I don't know that I'm going to be pushed through a 20 ohm and a 5 ohm resistor. All I can tell is that I've got 25 ohms of resistance to flowing in this circuit. And I feel that resistance here and here and here and everywhere, right? Because the resistance in series is just the total resistance, and the total resistance is the sum of these two resistances. So that's another rule of series circuits, and more so it's a rule of resistors in series. I'm going to put that down as rule 3. R's in series add. That is to say, if I know the value of this resistor in series with this resistor, I can model them in my head as one resistor. So I can think of this circuit as simplified to this circuit with a 25 ohm resistor. See how I did that? 20 plus 5 is 25, easy enough math, still 100 volts. This is the equivalent circuit to this. This is the equivalent resistance to these two resistors. So with that in mind, I'm going to do some math over here on the left-hand side. It's easy math. I'm going to say that RT, our total, equals R1 plus R2. And that's going to equal 20 ohms plus 5 ohms, and that obviously equals 25 ohms. So that's the longhand for my shorthand is RT equals 25 ohms. So now I've got values I can work with in Ohm's law. Suddenly I can say I've got a 100 volt source and I've got the equivalent of a 25 ohm resistor. So I can now solve for current. And this is the exact same way you're going to do every series circuit. If it's a series circuit, you're going to find the total resistance, you're going to mark that down, and then you're going to run this function of Ohm's law to find out what the current is. Solve for current. Again, I got my eagle, my individual, and my rabbit. I cover up the I because I is current, and I'm going to have left over E over R, and that's going to be 100 volts divided by R, in this case, is R total. I should mark that, 25 ohms. 100 divided by 25 is going to be 4 amps. Don't even need a calculator for that. So now, I've got 4 amps. Now, am I done? No, I'm not done. Because that 4 amps is going to travel through this resistor, it's going to continue going this way, and it's going to go through this resistor, and down to here, and it's going to stay at 4 amps. That 4 amps is the same 4 amps everywhere in the circuit. Not only is the value the same here and here, but it's the exact same current. The current I see here is the current here. If I take one of those fancy amp clamp meters, I don't know if any of you have those, your little fluke that you put around a wire and it gives you the current. That thing is going to show me 4 amps if I hook it on there. It's going to show me 4 amps if I hook it there. It's going to show me 4 amps if I hook it there. It's not only an equal current, it's the same current. I see the exact same current flowing everywhere in this circuit because it's flowing all at the same time. It's like, again, marbles in a tube. They're all pushing through at the same rate. In order for this one to move, it's got to push the one in front of it, which pushes the next one, ad infinitum all the way down the line. So with that 4 amps, now I'm using this rule number 2 here to do this. Current is the same at all points. That means that at this resistor, at R1, not only do I have 20 ohms, but I have 4 amps. At R2, not only do I have 5 ohms, but I have 4 amps. So here's the cool thing. I may be putting 100 volts on this circuit, but that 100 volts doesn't stay the same everywhere like the current does. The current is the same everywhere, but this 100 volts actually incrementally drops, because if I'm measuring voltage, remember I said this whole point compared to ground is 100 volts. Well, this point here is going to be something less than 100 volts to ground, because I've dropped some voltage across this resistor. When that resistor does its thing, it resists the flow of current, it creates heat, it actually uses up some of it, doesn't use up some of the voltage, but we see a drop in voltage on the other side. That is to say, the pressure, the electric pressure, decreases between here and here. It's like a pressure regulator almost. So I've got 100 volts here, I've got something less than 100 volts here, and then by the time I go here, I should have 0 volts, right? Because this whole point is 0 volts. So we call those voltage drops. And we actually say that when we have a series circuit, we call it a voltage divider. I'm going to explain that a little bit more. Voltage divider. That is to say, I take a voltage and I divide it proportionally between the resistors that it encounters in series. Now this only works for series, and it's only series circuits that are voltage dividers. Next week we're going to find out that if I have a parallel circuit, it's actually a current divider, and the voltage stays the same everywhere, but that's moving ahead of things. For now, a series circuit is a voltage divider. Now, I've listed these in 1, 2, 3, 4 order. These aren't necessarily, this isn't like the second rule of series circuits or the third rule. It's just the order I happen to be talking about them in. But they are good, all rules of series circuits. It is a voltage divider. Here's how I can figure out what my voltage is, because I can go back again to these individual resistors. I'm going to draw a box around this one, right? So this is my R1. Now at R1, I know I have 4 amps because I have 4 amps everywhere. That's that second rule, current is the same at all points. I use that rule to apply that current individually. Even though that current exists everywhere, I'm going to say, whoa though, I'm going to focus in on this guy, because you know what, that 20 ohms doesn't exist everywhere in this circuit, and whatever the voltage drop is here isn't the same as everywhere else in the circuit. So I'm taking that one quality that is the current in this circuit that applies everywhere, and I'm applying it individually. So I'm going to run Ohm's law in here. So I've got my R, this is my R, right? And I've got my I. I want to solve for E, or voltage at this, across this resistor, or we say dropped across this resistor. And for me, when we talk about it, you might hear me saying voltage at the resistor, voltage dropped at the resistor, voltage across the resistor. It's all the same thing. It's just 3 different ways to say the same thing. That is to say, if I took my voltmeter and measured across this resistor, how much voltage would I get? And it would be the difference between this point and this point. It wouldn't be the difference from that to ground. It would be the difference between here and here. That's how I would measure it. But let's go ahead and solve it. I know that E equals I times R. If I cover up my E, I go I times R. I know I is current, R is resistance. I've got current, I've got resistance. So again, doing the math down here, E at R1, because that's the voltage at R1. You guys are going to have to get used to that sort of nomenclature. E at R1 equals I at R1, which is I everywhere in this circuit, in a series circuit. So I really don't even need to denote that. I can just say I times R1, which in this case is 4 amps times 20 ohms. And that gives me 4 times 20, 80 volts. So I've got a drop right here of 80 volts at R1. And if I asked the question on a test or a quiz, I would say E at R1 equals blank space. And if you got the correct answer, you would fill in 80 volts. E at R1 equals 80 volts. Now let's do the exact same thing at this resistor. This resistor has 5 ohms and 4 amps. Now it's the same 4 amps, but I'm applying it individually to this resistor. So again, E equals I times R. And I really recommend you guys write out the formula every time. It'll keep your mind straight in what you're doing. It'll also force you to memorize them. So you'll just automatically say, well, E equals I times R. And R equals E divided by I. And blah, blah, blah. So E equals I times R. E, and this is R2. I is the same everywhere, right? I is going to be 4 amps times 5 ohms. And I can do 4 times 5 in my head, and E at R2 equals, what's 4 times 5? It's 20, isn't it? Not 40. Oh yeah, you can do it in your head, Jack. Equals 20 volts. So E at R2 is 20 volts. So we've solved that guy. Let's see if I can draw a box around this one. Boom. Those are my 2 resistors in series, and we've solved essentially all the values we need to for them. We'll get into power a little bit more in a bit, but I want to stick just with voltage, current, and resistance for the time being. Now here's a really cool thing to see, and it's actually the 5th rule of series circuits. And that is a thing called Kirchhoff's voltage law. So Kirchhoff was this scientist. Your book might talk about Kirchhoff, I'm not sure. And he spelled, you don't have to spell it right, but I'll tell you, C-I-R-C-H-O-F-F. And he's got 2 laws. He's got a current law and he's got a voltage law. This series circuit is a voltage divider, so that's one way to remember. We use Kirchhoff's voltage law. Now the other thing to remember, if a series circuit is a voltage divider, then I can't have the same voltage everywhere. It must be the series it must be the current that's the same everywhere in a series circuit. Because if it's a voltage divider, it's by definition not the same everywhere. And I know that there's something in a series circuit that's the same everywhere. Well, let's see, a series circuit is a voltage divider, therefore it must be the current that's the same everywhere. And we'll be able to do vice versa when we get to parallel circuits. But for now, remember, current's the same, series, it's a voltage divider, and we're going to use Kirchhoff's voltage law. And Kirchhoff's voltage law is just a demonstration of this. Check it out again. I've got a voltmeter, and I'm measuring my voltmeter. These are my probes, okay? Right here, my voltmeter is at 100 volts. As I move around the circuit, I'm still, because I'm between 100 and 0, nothing has changed, right? But as soon as I pass this 80 volt drop, it's the same as taking 80 volts off of this 100. 80 volts off of 100, or 100 minus 80, is 20. So if I measured from here to here, I would now have 20 volts. And as I continue going, look at that. I got 20 volts left. I drop the rest of the 20 volts, and I'm at 0. So there's 2 different ways of looking at this phenomenon. You can say, well, my 2 voltage drops, in this case 2 because there's 2 resistors. If there were 3 resistors, there'd be 3 voltage drops. If there were 127 resistors, there'd be 127 voltage drops. However many voltage drops I have, if I add them all together in a single series circuit, they're going to add to the source voltage. In this case, it happens. 80 volts plus 20 volts is 100 volts. Another way to look at that is they subtract to 0. And that's, a lot of people will either say they sum to the source or they subtract to 0. If I start at 100, I'm going to drop 80 volts. I'm going to be at 20. I'm going to drop another 20. 20 minus 20 is 0, and it should be back to 0 here. And that works in any series circuit. And the cool thing it shows us is, if that's the case, if I measure from here to here, I've got 100 volts, right? So this is all at 100 volts compared to ground. Now if I drop 80 volts and I'm still measuring compared to ground, I'm at 20 volts everywhere here between the resistors to ground. And if I drop that 20 volts, I'm at 0 volts. Well, check it out. I can use instead of measuring everything to ground, if I now measure just between this and this, I measure from 100 to 20. 20 to 100. Remember, voltage is difference between 2 points. The difference between 100 volts and 20 volts is 80 volts. So some of this might be obvious to you as you're looking at it, but I'm just pointing out all the obvious things in case it isn't. That's how voltage drops work. Same thing here. I'm at 20 volts to ground and I'm at 0 volts to ground. The difference between 0 and 20 is 20 volts. And in fact, that's how much I drop there. Now again, 2 really easy resistors with really easy values that add up to 100. It's pretty easy to see this. Later, when we've got 17 resistors in here of different convoluted values, it's really good to be able to figure out and see those drops sequentially and figure out what the voltage is between 2 different places. Because internal to a complicated series circuit, you're going to have all sorts of different voltages. So, last rule is Kirchhoff's, C-H-O-F-F's, voltage law And I'm just going to say all drops, all voltage drops, I should say, add to source E voltage. Sorry if my writing is getting tiny at the corner. The fifth rule is Kirchhoff's voltage law, and that is all the voltage drops add to the source voltage, which is the same thing as saying all of the voltage drops from the source subtract to zero. It's two different directions to say the same thing. So that's our first series circuit with more than one resistor in it. Let's do a couple more. Let me check my time because my video only goes for 30 minutes. And, of course, I got 2:37. I'm going to end this video and do another one.